देखो, now we are going to discuss about electrical materials. Okay, in electrical materials, as you can see, we have the conducting material, magnetic material, insulating material. Electrically conducting material, these materials carry current in an electrical machines. Electrical conducting material is the material which carry current in an electrical machines. So one is highly conducting material. What are the highly conducting material? That is copper, aluminium, gold, silver. These are all what? These are called the highly conducting material which we used in the windings. Okay, second is a highly resistive material. Highly resistive material is alloys used in a heating element. Okay, how alloys are prepared? Alloys multiple material fused together, then the alloys we get prepared. Okay, suppose this is the structure of material. Okay, once you add the other material, crystal structure changes in alloy. The crystal structure of any material changes in alloy, and atom change their position. What are the atoms? What they will change their position? Electrons will collide with atom, so current will not be carried to one place to another. Okay, so it is a highly resistive material. Alloys are the highly resistive materials. Okay, one more important thing is alloy temperature coefficient is low. Alloys has a very low temperature coefficient, where you can see r equal r r equals to r naught 1 plus alpha del T, where alpha is the temperature coefficient of resistance. So alloy has the low temperature coefficient. This temperature coefficient of alloy is low. Properties of highly conducting material. These are the highest possible conductivity, means it is very conductivity, less temperature coefficient of resistance, adequate mechanical strength, it should have adequate mechanical strength, and absence of brittleness, छिटकना, जल्दी वो छिटक ना पाए. ठीक है, कॉपर को वायर को जब हम लोग वाइंड करते हैं तो एक संग वाइंड रहे, वो तुरंत अपने पेस को छिटक ना जाए. ठीक है, उसका मैकेनिकल स्ट्रेंथ बहुत ज़्यादा होना चाहिए. Rollability and durability should be there. Rollability and durability should be there. We can roll that material and we can draw into any shapes. Should be there. Cooled weldability and solderability to ensure low resistance of the joint. It should have the cooled weldability and solderability to ensure low resistance of the joint. Adequate resistance to corrosion. It should have adequate resistance to corrosion. Copper machine. Copper, why we use copper we use for making a machine windings. Okay, the conducting order is what? Aluminium is more conducting, gold is more conducting, gold is more conducting than silver, and silver is more conducting than copper, and copper is more conducting than aluminium. Okay, so this gold and silver is very costly. These two are very costly, so we are not using these two. Okay, conductivity order. This is the conductivity order. As you can see here, is means first gold is more conducting than silver, silver is more conducting than copper, copper is more conducting than aluminium. As you can see, as gold and silver is very costly, so these materials are very precious and very rare available in nature, so we are not using gold and silver. Okay, okay, it is, and copper we are using. It is used to construct windings of an electrical machine because the cost is not very high and it is highly conducting. Copper, why we are using it is there, we are using for making the windings of an electrical machine, because the cost is not very high and it is highly conducting. Copper is resistant to oxidation and corrosion. It is resistant to oxidation and corrosion. Hard drawn copper wires are used in this is the process. Okay, hard drawn copper wires are used in electrical machines because their mechanical strength is very high. Temperature coefficient is 0.0393 degrees Celsius. Okay, okay, this is the temperature. This is a low temperature coefficient, but alloys has more low temperature coefficient than the copper. It should be in the multiple of 0.000. Okay, so alloy has a very low temperature coefficient. Copper itself also have a low temperature coefficient, but if you compare to alloys, copper has a more temperature coefficient than alloys. Now coming to aluminium. Since copper is getting depleted, now copper is also getting depleted. Aluminium is the next best choice for conducting material as it is abundantly available. As aluminium is Abundantly available means it is more available than the copper. So we are shifting to use the aluminium. Okay, aluminium cannot be drawn into the wires, but it can be used to form the seat. We cannot make a wire with the aluminium, but we can make a seat with the aluminium. Okay, what these are the parameters. Cost: if copper cost is 1, then copper cost is 100, suppose 1, then its cost will be 0.49. Crossover cross section area: if copper cross section is area will be 1, okay, then it should be 1.62, it should be more. Okay, diameter 1, then 1.27, volume 1, then 2.04, volume will be weight 1, but it is a light as compared to copper. 0.49 strength: suppose if strength is 1, then it should be 0.64. Its mechanical strength is less than the copper aluminum, and moreover it is lighter than the copper. Okay, see, copper conductivity is greater than aluminum. Suppose we want to keep the resistance same of by what we are making the materials. Okay, sheet. Okay, R equals to rho L by A, L by sigma A, rho 1 by sigma. Okay, so sigma. So R copper equals to R aluminum. Okay, both resistance we are making the same. Ba 1 by 1 L by L by, as you can see, L by sigma Cu, aluminum Cu. Okay, so if Al, if you brought here and multiply, so sigma C by sigma Al into ACu. As you know, copper conductivity is greater than the aluminum conductivity, so cross sectional area of the aluminum is greater than the copper. Cross-sectional area is greater than the copper. Why cross-sectional area of aluminum is more than copper? This is the first question you can note. Why cross-sectional area of the aluminum is more than the copper? Because copper because copper conductivity is greater than the aluminum conductivity, so cross-sectional area of the copper is so cross-sectional area of the aluminum is greater than the copper. Okay, see this is the machine. Okay, for aluminum wires, the size of slot required is higher as compared to copper. These are the slots for aluminum wires. Okay, wires or seat or any wires, what size of the slot should be bigger. Okay, should be bigger because the cross sectional area of the wire is higher for the aluminum. For induction motor above 100 kilowatt output, aluminum can be used for cage rotor. For induction motor above 100 kilowatt output, aluminum can be used for a cage rotor. Aluminum can be used to form a foil type low voltage winding in a transformer. It can be used to form a foil type low voltage winding in a transformer. In a transformer, it can be used to form a foil type low voltage winding in a transformer. Aluminum can be used to construct a tank of a transformer to reduce stray losses. This is the very important point. Okay, this is a very important point. Aluminum can be used to form the tank of a transformer to reduce stray losses. Aluminum easily get oxidized to form Al2O3 layer, which prevents further oxidation. Corrosion. How the corrosion is less? Why the corrosion is less in aluminum? Because aluminum easily get oxidized to form Al2O3 air. This layer further prevents the oxidation. Okay, now moving to the electrical carbon. Electrical carbon. This material is made from a graphite and other form of carbon. Electrical carbon is made from a graphite and other form of carbon. Conductivity of carbon is less than copper and aluminum, but its surface is smoother, so it is used to make brushes in an electrical machine. And sparking will not happen because friction will be reduced that time. The surface is smoother, sparking will not happen, and friction will be minimized. Okay, so we are using the carbon, whereas aluminum and copper has a rough surface, so we cannot use to make the brushes. Aluminum, copper have the rough surface, and whereas the carbon have the smoother surface. Okay, so we are making use of it to make it to make brushes in electrical machines. Okay, carbon brushes are graphited or heat treated. Why it is a graphite or heat treated? To increase the conductivity and reduce the hardness. Okay, for increasing the conductivity, what is it? It are graphited or heat treated. It are heat treated to increase conductivity and reduce hardness. Material, if we heat, the molecules will move far distance and electrons can easily flow in it. So we can increase the conductivity of the carbon by the heat treated method. Okay, graphite has a negative temperature coefficient. It has the negative temperature coefficient. R equals to R naught 1 minus plus into minus alpha del T. As temperature increases, if you increase the temperature, what will happen? Resistance will decrease. Okay, so suppose current is flowing, loss will happen as the loss temperature increases but resistance decreases. Current flowing, loss will happen, temperature increases, resistance decreases. Brushstroke IR is kept constant because current is increasing. Current increases, resistance decreases. So this parameter is kept constant. Brushstroke is kept constant because why? Because graphite has a negative temperature coefficient. If temperature increases, resistance decreases. So brushstroke which is higher temperature, current increases, losses increases, temperature increases, so resistance will decrease. So it is kept constant. Okay, copper windings we use for making windings. Aluminium we used for making transformer tank. Carbon we used for making brushes. Now moving to the next material, that is magnetic material. Okay, the materials that allow the flow of magnetic field through them are called magnetic material. The material which allows the flow of magnetic field through them is called the magnetic material. Diamagnetic material. Dia Diamagnetic material. No dipoles in absence of magnetic field. No dipoles will be made in absence of magnetic field. Once an external magnetic field will be applied and if diamagnetic material there is no magnetism in absence of external magnetic field. When magnetic field is applied, dipoles are induced and they orient in a direction opposite to magnetic field. What will happen whenever an external magnetic field is applied? A dipole will be induced in a diamagnetic material, and these dipoles and 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 these and they orient in a direction opposite to the external magnetic field. So internal magnetic field be what? Internal magnetic field of this diamagnetic material is opposite to the external magnetic field. Okay, as you can see in a magnetic material, what there are two poles will be there, north south. Inside the material, the magnetic field lines will flow from south to north, but from outside the material it will flow from north to south, as you can see here in this picture. Next, moving on. Magnetization. What is magnetization? Ability of a dipoles to align when magnetic field is applied. Ability of a dipoles to align when magnetic field is applied. That is called magnetization. Okay, ability of dipoles to align when magnetic field is applied. Magnetization is equals to x and h. X, and that is called chi m h. Chi m is what? It is a magnetic susceptibility, and this h is the external magnetic field. Okay, chi m is a measure of a material to get magnetized when external magnetic field is applied. It is a measure of the material to get magnetized when external magnetic field is applied. Okay, diamagnetic material. In diamagnetic material, magnetization and external magnetic field are opposite. So chi m, external and magnetic field are opposite. So chi m is less than 0. Chi m is negative. Relative permeability. Relative permeability. Relative permeability is a tendency to allow magnetic field. So mu equals to mu 0 mu r. Mu 0 is the permeability of the free sphere, which is equals to 4 pi into 10 to the power minus 7 Henry per meter, and mu r equals to 1 plus x by m. Tendency to allow magnetic field. Mu r 1 plus chi m is less than 1. Okay, less than 1. So mu is less than mu 0. Mu is less than mu 0. Okay, permeability of a material is related to ability of a material to allow magnetic field lines to pass through it. Permeability is the ability of a material to allow magnetic field lines to pass through it. Magnetic flux density. Magnetic flux density represents the closeness of magnetic field lines to each other. Magnetic field lines equals to mu h. In diamagnetic material, what will happen? Mu permeability of a diamagnetic material is less than the mu 0 permeability of the free space. So what we have? Magnetic field lines magnetic flux density in air is greater than the magnetic flux density in diamagnetic material. As you can see, flux density in closeness of magnetic field lines. Okay. In diamagnetic material, it will be far. Closeness will the distance into magnetic will be greater as compared to the magnetic flux lines in an air, as you can see in a figure. Because why? Because because permeability of the free space is greater than mu. Permeability measures the ability to magnetic field line to pass through it. So in air, more magnetic field lines will be passed through it, but diamagnetic material, less magnetic field lines will be passed through it. Okay. In a diamagnetic materials, magnetic field lines diverge away from each other. They diverge away from each other. In a diamagnetic material, magnetic field lines they diverge away. They will be diverged away from each other. For example, copper, silicon, germanium, gold, diamond. These are all what? These are all diamagnetic materials. Most important, copper. Copper is a diamagnetic material in which the magnetic field lines diverge from each other. Okay. Now coming to the paramagnetic material. In a paramagnetic material, magnetic dipoles already exist due to spin of unpaired electrons in an atom. Paramagnetic material, magnetic dipoles already exist due to an unpaired electrons in an atom. Okay, these are the paired electrons, these are the unpaired electrons. Due to these unpaired electrons, what will happen? Paramagnetic material, the dipoles will be there, already exist. Spin does not cancel magnetic dipole. Okay, here spin does not cancel magnetic dipoles. Okay, south to north. Okay, south to north is shown as an arrow. Okay, south to north, south to north, south to north. If external magnetic field is is zero, then these dipoles will be like this. If external magnetic field is applied, then what? Dipoles will align in the direction of the external magnetic field. Okay, so its internal magnetic field will be same as the external magnetic field. In paramagnetic material, magnetic dipoles are randomly oriented, but when magnetic field is applied, such dipoles align parallel to external magnetic field. Such dipoles will align parallel to magnetic. In paramagnetic material, magnetic dipoles are randomly oriented, but when magnetic field is applied, such dipoles align parallel to external magnetic field. Okay, M equals to xm h m is in parallel with h, so xm is chi m, which is called chi m, not xm, chi m. Chi m will be greater than 0. Chi m is greater than 0, the mu r is 1 plus xm should be greater than 1, should be greater than 1. So mu equals to mu 0 equals to mu r is greater than mu 0. So B air equals to mu h. So B para mu 0 mu r s is greater than B air. Okay, due to positive susceptibility, the flux density inside paramagnetic material increases. They will increases. The flux so here, closeness will increase in a paramagnetic material because chi m is positive due to positive susceptibility. Example of this paramagnetic material are potassium, oxygen, tungsten, and other and rare earth metals. So mu r for dia and paramagnetic material, mu r is the relative permeability, which is equals to 1, which is equals to 1, which is considered as a 1. Thank you. In next video, I will tell you about the ferromagnetic material. Thank you.